with the tools that we've developed so far, we're going to look at some more specific applications beyond extending what we did to rotation. We're going to actually look at some. And the first one is a situation that's actually a little easier than ones we've seen before, and that is a situation where we're looking at an object in equilibrium. In particular, in static equilibrium. So it's, we're going to look at generally things that are at rest. And so for something to be in equilibrium or to be at rest, then we would say its acceleration, the acceleration of the center of mass, is equal to 0, and its angular acceleration is equal to 0. So what this means is that the sum of all the forces that act on the object must be equal to 0, and the sum of all the torques must be equal to 0. And these are often called the first and second condition for equilibrium. And you use both of them to sort of figure out what's going on. So you can use this, for example, if you think about balancing something. If you think about mobiles that are sort of set up where you've got a mass hanging off of here, and then a mass that hangs off of here. Then how do these balance? Well, if this is a longer arm than this, then you figure that this is a smaller mass. But you can extend this sort of down to include additional masses here and here. And so what you would do is, for example, say, let's take this point or even maybe this point, find the torques around this point, find the total mass, and then you'd find out how much tension. So you draw a force diagram. So for the sum of the forces, we would say, okay, the tension up here must be equal to the weight of this entire thing. That would be M1G, M2G, and M3G. So this tension must be equal to these two. You can find the tension here. Tension 2, you can say, is equal to this mass pulls this mass, so you're using F equals ma for all of those. And then, so that would be your F equals ma equation. So that would be tension, the total tension, which should probably be bigger, is equal to M1 plus mg, M2, mg plus M3, G, which you could have written as tension minus all of this equals 0, right? To say the sum of the forces equals 0. And you could have an ancillary equation that is T2 minus M2G minus M3G is equal to 0, and that would allow you to solve for T2, for example, if you wanted to do that. You might be solving for the mass, you might be solving for the tension. It's hard to know. It's sort of the question of how much mass do you need to put down here, for example, to balance all of this out. And then the torque equation would look like, well, this might be my R1, this would be my R2, and what we're going to do is call one of these torques positive and one negative. So if you look at this one, this makes it rotate that way, and then this one makes it rotate this way. So we could call this one positive, and the torque here, so the torque equation right up here would be R1 times the force M1G down, if we're doing the torque around that point, looking to see that it's balanced, and then I would say minus R2 times T2 must equal 0. And then I can do a similar torque equation right around that balance point if I'm trying to find something associated with that. And so this is the way we use these conditions of equilibrium to set up a balance or to test to see, oh, is this going to break? Is this going to break? Is this going to balance or not? Okay, so this is a balancing kind of situation when we are looking at things that are just going to be in equilibrium.